So the title is New Technologies in Energy Sector as a response to the challenge of the European Green Deal. Everyone telling and discussing about the European Green Deal. So in the European Green Deal, we can distinguish following actions like climate, energy, agriculture, industry, environment and oceans, transport, finance and regional development, research and innovation. So if we are talking about power electronics or generally electrical engineering, so we can distinguish here at least for sure this action as energy, but we can find our place also in industry, we can find in transport and for sure research and innovation. But at least I think that we can find our field of research and our field of activity also in another actions of the European Green Deal. But I distinguish for today, for this lecture, 5 actions which are, I think, the hot topic recently, and also it's a hot topic for the future. So I distinguish new energy sources, energy storage, electromobility, green hydrogen, and smart grids. And I think that all of them, they are very good field for power electronics guy. So I think that you were born generally in very good time, because for sure, especially what it happened now that we have the crisis, energetic crisis, that the demand for our activity will be at least for the next 50 years. So as I told, that it's a really good time. So let's focus first on the renewable energy sources. Generally, you can see how is the prediction of the change of the energy mix. So it's 2014. You can see that most of the energy is based on the coal. Then renewables was 23%, but this energy mix, the prediction, it's forecast that will be changed like here, probably even more after what happened in February this year. Probably that renewable will be even more important for this energy mix. But moreover, what it's also have to be considered, that have a look. We are providing all the time the new technologies saving the energy, more energy efficient. But still demand of the energy is growing. Why? Because there are 2 reasons. First reason is the population is growing. We have currently we have 8 billion of people living, and soon I think will be 10, maybe 15. So those people, they demand the goods. If they demand the goods, we have to produce more and more. And there are 2 questions appears. First, what about the resources? When some of the materials are still currently very demanded on the market, and they are not available, but the demand is very high. And another also the problem with the energy, where we find the energy to supply all this big population. I think that's a problem which have to be. It's a problem which have to be solved by many fields of the research, but one of the most important is the field of the research for electrical engineers. So for sure this energy mix be changed. Also we have to take in account that of course the potential of renewable energy sources is very high. You can see this here on the left, this dark blue. There are potentials including the biomass, hydro, solar, wind, geothermal, ocean, and on the right there are used, which is not too high. So you can see that potentially there is a lot of possibilities to produce the energy from the renewable energy sources. And also we have to look for some of the reserves. This is what I told just with the previous slide, that we have to think how we'll produce the energy, not today, but after 20 years, after 50 years, after 100 years. Taking into account that we have some of the limited reserves. There are some of the predictions. Of course, those predictions depends on the source, can be slightly different. However, the one message which is here, the first of all, the potential, because there a lot of energy coming from the sun, and we should take this energy, because in fact all of those possibilities, they are energy from the sun. Yes, because the wind, it's also it's a reaction for the sun, and also biomass and geothermal and ocean and so on. So this is one message, and the second, that we should have some of the forecasts for the future, not only, as I told, for 10 years, but 20, 50. Okay, and one of the, of course, now the possible option is the PV. And you can see how was cumulative installed PV capacity starting from 2010 to 2020. And you please pay your attention that, have a look how China did good homework. Because in 2010, the China is almost not existing, then rapidly growing the number of the installations. The rest of the countries, slightly, maybe North America changed a little bit, improved the situation, Japan slightly, but other countries are not so active. So as I told that unfortunately we start to develop the power system based on the resources a little bit too late. What current situations show us that if the politicians, if the other authorities could understand earlier that how important, how independent situation gives the opportunity to install the resources, then I think we will be not in this situation currently. Moreover, that we can see some of the top 10 largest solar PV plants in the world. So have a look. The first one in India, 2.7 gigawatt. So 2.7 gigawatt, it's like a big power plant, classical power plant, because usually generators in classical power plant, they have the 50 megawatts, 1 gigawatt, but here it's a 2.7. Then on the second position, China 2.4, China 2.2, India 2, Egypt 2.6, China 2.5, and so on and so on. You can see that first 10, the power of the PV is over 1 gigawatt. Those PV systems can be, of course, used based on the power electronics conversion on different manner. Those big one, it's on the centralized system. It means that we have the string of the PV panels, then connected parallel. Then we have the high power DC-DC converter, which is connected to DC bus, and then bulky DC-AC converter connecting to the grid. So it's cheapest solution. However, also during the home applications, we can use the power electronics converter dedicated only for one PV string, like here, or also the microinverters. This group was active, very active in this field of microinverters. So it means that each small power converter is connected to single module. And some of the models configurations, including the PV module string connected through the DC-DC to common DC bus, or the serious connection, like here, to have the medium voltage DC bus. But of course demand here the sum of the isolation, otherwise we cannot connect in series as such a converter. Some of the example of the simple PV converter, it was done by us in our team. It was some of the projects with Polish company, Third. So the construction from power electronics point of view, it's very simple, because the simplest solution for such converter is just a boost converter, as here with diode bypass, and there is a H-bridge converter with the filter. But if you would like to increase the efficiency, then we should omit the transformer, which normally it's down here. But if we remove the transformer, there is a problem with the circulating current. If there is a problem with circulating current, then it's mandatory to use some of the methods to omit the problem. And exist many of the patents of the companies how to skip this problem. However, in our case, we could not use any of the existing patents. Therefore, we decided to play with some of the modulation here, plus additionally those filters to omit this problem with circulating current. But you can see the final product, which is, I think, quite nice. The control, it's usually also very simple for such converter, so I think it's quite easy to build such solution. In case of the DC-DC, so there is a maximum power point tracking, the simplest solution. Then, of course, it's based on the power estimation. Then it's current control inside as an internal loop, and then we control the transistor in the boost converter. In case of the H-bridge converter, when we estimate the phase of the voltage, then we control the DC-link voltage as an outer loop, and we control the current as an internal control loop, and of course the modulation. So it's a really simple system. However, doing this project, by the way, by testing it's on this top roof system, which you see here, we noticed the problem of the partial shading. Using the simple algorithm, we cannot skip the problem with partial shading. And then we start to read the papers, and there's also answer why good to be in IEEE, because we have the access to the eExplore, and we can find quickly, we can do the research in the papers about the existing solutions. Please believe me that when I was in 2000 in Aalborg, there was the library with the transactions, and I sit whole day, page by page, looking for the same papers. Then with a copy machine, so I make a copy, then I collect, big sets of the papers. But it took me like a week or 2 weeks or 3 weeks to make the survey among the existing solutions. Now in eExplore, it's easy. I think that we can collect the papers in 1 day. The other option is that sometimes it's too many papers, it's difficult to read all of them, or there's a lot of many of not good papers also, which unfortunately in those sets of the papers make more complicated to find really brilliant papers which help us to solve the problem. But when we did the research, we noticed that most popular solution for the engineers, there is a meta-heuristic methods to find this global MPPT. And after studied, we said, okay, it's too slow, it's too complicated. So therefore, we decided to use the simplest as possible method. It means the short circuit, the PV panels for some of the microseconds. Therefore, we call this method that there is it's a fast MPPT or ultra fast MPPT. The idea is that we use a special transistor, which is shown here, and we change the resistance of RDS, and changing quickly this resistance, we can scan the characteristic of the PV panels, also including the partial shading. So we can see that we have here the local MPPT, and we have a global MPPT. There is a play with the resolution, how many, of course, the samples can be used for that. But we notice that even if the sampling is only 50 kilohertz, and we can draw this characteristic like those points, so we can show that highest point and then use the classical MPPT method to adjust the MPPT. Okay, now we move to the wind. Because as I told that this part belongs to the renewable energy resources. So you can see that also I think it's the most major technology start many years ago, and currently there is over 700 cumulative 700 gigawatts all over the world. However, you can see some of the trend that currently the offshore applications start to be more and more attractive, and even in Poland, but I think that generally in the Baltic countries, they are trying to install the wind turbine offshore. Why it's so important to install them offshore? Because the airflow is more laminar on the water, because if they are installed on the ground, there are some of the turbulences, even on the high elevation, like 18 meters, there are some of the turbulence. So it's more laminar flow. If there is more laminar flow, it means that we can produce much more of the energy, what is, I think, very crucial. And there is some of the social aspects that the people don't like too much. The wind turbines located close to the houses. So I think that this trend installing in the Baltic Sea, I think it's very good. And a lot of companies now invest the money in Poland to build this. And the size of this turbines, it's also growing. So the 2 years ago or 3 years ago, the record belongs to the Vestas, which was 9.5 megawatt. But now it's even more. Currently it's 12 or even 15, but it's going to the direction of 20. But the question is, because on the onshore, the most popular, I think, the power is around 3.5 till 5 megawatt. The question is why? Why not 10?
Such problems?
Why not 10 megawatts on the onshore?
Onshore, because of the previous problems that you mentioned, turbulence or?
It's not fully, of course. As I told, that production is slightly lower, but it's not most important problem to install the higher power.
Maybe people don't like to see that's a big turbine close to city.
Utilization.
What?
Utilization.
No.
Noise pollution.
I think it's a logistic problem. How to move the one blade, which is a single element, from the place where they were produced to the place of installation. There is a problem, because then when we consider there is no tunnels to move such blades, there are roads with the bends which are not permit you to move such blades. Therefore, onshore, there is limitation like 3.5 and maybe until 5 megawatt. But if we are discussing the offshore, there is no problem, because those blades can be produced just on the seaside. We can use some of the ships to move those even 20 megawatts, the blades for the 20 megawatts turbine easily. There is no problem with roads, with bends of those roads, with the tunnels, nothing. Therefore, you see that it's very promising, this offshore installation. Of course, in my group, we are not building the megawatt system. We are building on the kilowatt system of wind turbines. However, I think it's a nice example because, as I told you, that in case of the onshore installation, especially in small wind turbines, this problem of the turbulence, it's even more important, and it's more difficult to control such a wind turbine. So our experience is based on the multi-blades wind rotors, with the permanent magnet synchronous generator, with induction generators. We construct the permanent magnet synchronous generators with the minimize the cogging torque in the generator, which is very important, especially to produce the more energy when the wind is very slow. Yes, because usually on the land, close to the house, the wind speed is very slow, and the turbine have to be optimized for this low wind speed. But we construct. You can see that there was installed in some of the places, in some of the locations, full power electronics, full system, which is the power electronics is only part of the full system, but it was constructed. Okay, some of the other projects which we did many years ago, but I like very much to show that it's some of the opportunity. They are opportunity to produce the energy from waves. Those digits shows how many kilowatts per 1 meter of the length of the waves can be produced. So you can see that some of the countries on some of the location, like close to Chile, for example, there is a 70 kilowatt. New Zealand, it's 100 kilowatts, and Australia here it's a 70 kilowatts. So the potential is really high. Also, there exist plenty of the patents all over the world showing that there are different ways to produce the energy from waves. What is a competitive solution to offshore wind turbines, especially in the places where the ocean or sea start to be suddenly very deep, and there is difficult to install the offshore wind turbine. In our team, of course, as I told, there's plenty of the solution. Our team participate in this project called Wave Dragon, which was in Denmark, with collaboration also with Aalborg University. So you can see how that simple assumption how the system works. So the waves coming, they increase the elevation, they overtop double curve ramp, and the water is collected in a reservoir, and the water then goes to the outlet, to the sea, running the turbine. And the idea of this simple solution, I think the simple solution was that if we even have the energy connected with waves like 48 kilowatts per meter, then 1 unit of such unit can generate 35 gigawatt hours per year. So I think it's, as I thought, it's competitive to the offshore wind turbine. So you can see some of the photos showing when there was no waves, so no energy production, and there is energy production, and the generators are located in these tubes. So also it's important to keep the proper level of the water in reservoir, so those tubes are on, off, just to control the level of the water inside the basin. However, it works, and I think maybe it's a technology of the future. So now we move to the energy storage. So you can see different technologies. By the way, in each slide which I can deliver you, there is a reference to the paper, and notice that the colleagues from TalTech, they are co-author of this paper. So it's our common achievements, but you can see that technology of generally of energy storage is a hot topic now, especially that we have a different technologies like compressed air, flow batteries, sodium sulfur batteries, lead batteries, also we have a flywheel and so on. There are plenty, but they are here it's collected as a high energy capacity, so it's this region, and fast power response. This is those energy storage, but you can see that this technology is really promising. And again, if we developed this technology 10 years ago and we'll have more installation now, probably we'll have less problem currently with current political situation. Also, there are some of the pictures from the past showing that such system, they are installed close to the different PV park or the wind turbine parks, showing that some of the technologies like sodium, lithium, they are installed, and you can see the capacity like 300 megawatt hours, 120 megawatt hours. So you can see that there is a future. Even in Polish traction, in Polish trains, there are a lot of projects installed energy storage to the power subsystem, because the idea is following. Normally, if there is like a fast train which has a power like 7 megawatt, demand the connection of 7 megawatt, but the train is going, for example, once per hour. Yes, just one train go, the distance of 5 kilometers and disappear. But the connection of 7 hours is still delivered. And this is a high cost of those railway operators. So railway operators decided, okay, so let's reduce this power connection to, for example, 300 kilowatt only, install the bulky energy storage, and if the fast train is going through this distance of 5 kilometers between the two stations, then the energy is taken from the battery, what reduced significantly the cost of the energy. And there is a lot of projects now related to such installation. However, this energy storage can be used for different purposes. One of that is that we can move the energy and storage the energy during the night hours to hours where the peak, like here. We can also have the opportunity to charge and discharge capacity firming, like here, and we can stabilize the frequency, what you can see here. So there's a lot of opportunities which can the energy storage can be used. And it can be not possible everything without the power electronics. So you can see that there are a lot of opportunities like single stage conversion from AC-AC or to AC-DC, DC-AC. So different opportunities to connect our energy storage system, all of those energy storage systems, to the grid. Therefore, as I told, we are living in the golden era of the power electronics now. And I think this golden era will be next at least 50 years, because we are more and more depicted to the electrical energy. There are some of the new topologies. So these new topologies are based mainly on the modular multi-level converters. So you can see different research fields, including the one bulky storage elements connected to MMC, or the small energy storage system connected to each cell, like here in high bridge or chopper cell, which are installed here in this one module. So there are plenty of the research fields. So generally, my message here is that power electronics give a lot of different opportunities to do the PhD, different opportunities to do the research. It's like Amazon River. When you try to go to the roots, there are plenty of the roots, and each of you can find the opportunity to find a really nice, interesting topics to do your PhD. Moreover, the price of the batteries. Here you can see the lithium-ion battery price, which dropped almost 10 times since 2010 to 2018. What was also motivation to develop the system, energy storage system. But the more forecast, the more prediction is that even in 2030, the price for 1 kilowatt hours will be only $62. So I think that also it was one of the motivation how to improve the research generally connected to electrical engineering and install the energy storage to the power system. The shame of the Europe is that many years ago, Europe was the leader in the energy storage, in the batteries. Then Europe completely forget about this. And what happened that currently only 3 countries has a technology to produce the batteries. It's Korea, Japan, and China. And after many years, then again the Europe wake up that, oh, it's really promising, the batteries, it's a promising technology. However, we not develop, we invent this, but we not developed last years. And they start to recover now the research, especially the European projects. Many of the European projects now currently dedicated to this technology. And in Warsaw University of Technology, you can see the sets of the projects. Only the battery projects which are related to change this situation. And what it's promising that when now the European Union start to invest the money for this market, again the Europe start to be the player in the competitor in this technology. Of course, still there is a big gap between the Asia and the Europe, but we hope that thanks to these projects we can change the situation. One of the example of such projects, which is realized in my university, in another faculty of chemistry, but they develop technology which is already commercialized by Arkema in France. But what's the advantage of this technology? They improve the thermal stability up to 250. They also increase the energy efficiency. They improve the battery safety and lifetime. Also, they lowering production cost. And what is very important, they 4 times decrease the amount of toxic fluorine. Usually there is a problem, as I told, to access to some of the materials which are not existing even in Europe. Therefore, it's important to build and to propose the technology based on the materials which are existing in Europe. But also they design novel cobalt-free electrode materials and design non-fluorine electrolytes capable to work with new generation high voltage cathode materials. And also we've increased the safety up to 300 Celsius. So I hope that in the next 10 years, I think the Europe be again a player in this technology of the batteries. Okay, electromobility. Electromobility I distinguish in 3 parts. Electrical drives, I'm not going to talk about this. I think it's a major technology now and nothing to do. Charger systems, they are also quite major technology, but the problem, it's the architecture of power system supply. Of course, we can build many of chargers, but if we have no power supply to connect them, they are useless. Therefore, there is a wide field for the old electrical engineers, not only for power electronics, but also for power system engineers, how to change the structure of power system, how to make more efficient system to charge our cars faster. Ultra szybki, it's fast charging, but I think that you can distinguish one word, Tesla. That's a bus, and there is the city car. Yeah, so city car has the lowest demand of the power. The bus has the highest demand of the power. And there is a time of charging in minutes, and there is a power. So we can see that if we would like to charge very fast our car or buses, then, for example, if there is a Tesla, in 15 minutes, then we demand the access to the power for the 400 kilowatt. And this is a problem. No one has such access to such power. And if we have many of the Teslas at the same time, connected to the same cable, there is rise the problem. But fortunately, we as engineers, because we know that we cannot change the situation quickly, but we can technologically extend, for example, the configuration of the system, including the PV, for example, on the AC or the DC system, thanks to our power electronics converters. Also, another option, which is again shows the battery, that we can charge the battery, and the battery is like energy storage for our cars. Of course, it can be done on the AC or DC or the DC side. But if we are talking about electromobility, there is not only the cars. You cannot believe that 80% of the goods are transported by ships, not by cars, by ships. And those ships are coming normally to the port. There are two options. One, that the diesel generators are all the time running, but those diesels, they are not comparable to the diesels we are using in the cars. They are much toxic, they are using the bad fuel, and there is pollution, it's really, really high. And all the time being in the port, generators are working. Other option is that, of course, they can switch off the diesel generators, but they have to be connected to the supply system on the shore. But the system is following. They are manual system. They are engineers. Okay, stop the diesel generators. They put the cable on the shore. They connect this to the transformer, and it takes like 1 hour to connect the ship to this shore system. Sometimes it's not easy because if there is some of the temperature fragile, goods on the ship, this system cannot stop for the 1 hour. But thanks to the power electronic system, you can see that we can use following, that there is a ship with this load, there is some of the switch, there is a converter, of course with transformer, and we can use it very quickly and very fast, and we did such project showing that we can do in the milliseconds, in fact. So we connect the system here. The converter is still not working. Of course, it's still working the diesel generator because it's diesel generator. So what the first converter is doing, he starts to generate. This is the voltage. By the way, maybe I will tell you what is here visible. So this is a voltage from diesel generator. This is the voltage from this converter in this point. So please pay attention that voltage from diesel generator is distorted because there are a lot of nonlinear loads on this microgrids which is on the ship. And then converter, it's following this diesel generator. So the voltage is the same distorted as the diesel generator voltage. Why? Because when we suddenly connect the system, so the harmonic, they have some of the influence for circulating current. Therefore, we distort the voltage from this converter to be the same distorted as here. And also, we adjust the amplitude of voltage. So in the beginning, this amplitude of voltage from this converter is much lower than from generator. Therefore, the current, you can see the system switch, it's switch on here. And then we increase the amplitude of this voltage, and it's more and more power is taken from the converter, but less and less power is taken from this diesel generator. And if the power is small enough, like below 10%, then the system, the diesel generator hits a switch off. And in very softly way, the ships, it's now connected and supplied from the shore. So this is also electromobility. Green hydrogen. Green hydrogen, it's a fashion now. In Poland, there's a lot of projects related to green hydrogen. I think that's a very nice figure showing how to produce, how it can be produced, the hydrogen, and how it can be used. Also, for us, I think it is this green one, it's most important. Of course, the production of the hydrogen, it's very simple, it's electrolyzed. I even remember in primary school, I did my experiment in my home producing the hydrogen, just a battery, salt water, then to some of the tubes, and then I produce the hydrogen. So the system, it's absolutely simple. However, all the time is the question of the price. How it's financially effective is production of the hydrogen. And another question that it should be the green hydrogen, because if we are producing the gray hydrogen, because we can produce the gray hydrogen, then it's still for the nature, it's not so good. Therefore, for us, it's an idea that if we have too much the energy from renewable energy sources, instead of, for example, to stop the production, because you can notice that, for example, there's a wind park, and in wind park there's 10 wind turbines, but only 2 are working. 8 are not working. Why? They are not a technical problem, because there is no demand for the energy. But if we could produce the hydrogen, then we can use all the time the 10 wind turbines is working all the time, but the energy from 8 it's used to produce the hydrogen. The same with the PV panels. If we have too much energy, then we have to move from the maximum power point a little bit to lose the maximum power point to produce the less energy, just because there is no demand for the energy. In such situation, we can produce the hydrogen. And for us, again, for the power electronics guy, there is a lot of opportunities, because you can see that the system of the hydrogen, including of course, there is a DC bus or AC bus. It depends which system we can select. There is a lot of power electronic systems, because we can use a DC-DC converter to control the electrolysis. Then, of course, there is compression, hydrogen storage. So this is our storage system. And then using the fuel cells, we can produce through our DC-DC again the energy, if this is needed. The same, of course, using the AC system. So I think it's also a good trend, and I think it will be the trend in the research in next 10 years in the European Union. My university, it's also active producing also this technology. Fuel cells. I think that the colleagues from different departments develop from single cell to stack, you can see, but also the new materials and so on. But I learned yesterday from Andrii that also in Estonia there is a big company producing the fuel cells. So I think that it's good for you to be in the contact in this company, because they demand also the power electronics. And what we discovered with one of my colleagues from my group, that the guys, the engineer for fuel cells, don't understand too much electrical engineers, and opposite. So be in close collaboration, because I think it's important to build a good product. And the smart grid. Of course, there is a huge opportunity for all of us, because the future electrical network will be like internet, including the many of the elements of production, classical, renewable energy sources, different system to storage. You can see there's a leaflet of European Union. So this European Union, this is a vision of European Union, how will looks the electrical network in the future, including all elements, even they include this, you can see this wave dragon here, which is the production of the energy from ocean waves. But you can find the PV, the energy storage, and so on. So because there is a huge potential, so you can see that a lot of research groups are working in this direction. So your research group is working in this energy router. So you can see that I distinguish that it's your achievement. But it's really nice, because it gives you the opportunity to connect the PV with storage for the classical AC system, or to have the hybrid system, including also the DC. So I think that it's a next step for the transformation of the AC system to DC system on this lowest level for the home application. In our case, in my group, we are on the level of the medium voltage. Therefore, we call that we are working in the direction of power electronics transformer, or smart transformer, or solid state transformer. They are different names in the publication and used by researchers. But generally, such system connecting the on medium voltage system with low voltage system give us a lot of opportunities. First of all, that we have a lot of terminals, because we can connect, some of the storages, electromobility, wind systems to the medium voltage DC. We can also connect to the low voltage DC. So there's a lot of opportunities. Moreover, that eliminates some of the power converters in the DC system here. We increase the efficiency because we have less energy conversion stages. What I think it's also important. But there are plenty of the advantages like that, because we have really advanced systems. So if there's after fault appears, that we can change the configuration of the system, and we can deliver the continuously energy to final client, which is here. So it means the final client and user never see that it's something happened in the system, because even if the failure is here, then we have some of the opportunities having batteries on the medium voltage side of the DC and low voltage side to deliver the energy to the final client. Moreover, that we can optimize the energy flow between these nodes in different levels to increase the efficiency of the system. So we are not depicted that all the time that the energy is taken from here. We can optimize the energy flow. Of course, it's very natural that we have some of the additional advantages, like we can control the reactive power, we can compensate the harmonics, and so on and so on. So I think that there are plenty of the advantages which are delivered by the use of the power electronics converters. Okay, let's move. So the simplest, of course, and most frequently used solutions is to use the cascade connected converters on the medium voltage side and parallel connected converters on the low voltage side, because here we have to capable to work with the high voltage and low current, and here it's a low voltage and high current, so the total power on the input and output it's the same. Usually it's done like this. So we have three-phase system, 15 kilovolts or the 20 kilovolts, it depends on the countries, and we can see these cascade connected converters. Then we have DC-DC converter in the topology input series output parallel, DC-DC with the high frequency transformers, and we have here the power connected converters as is shown here. But the final configuration, when we see that how many transistors are used, it's really impressive and difficult to control, especially that we have some of the, also included here, some of the redundant legs, because if the failure appears, then we should have opportunity for post-fault operation. What is important to convince the people from the power system operator. There are two difficult point. One, it's a continuous operation, because they not believe that power electronic system be so the same reliable as the classical transformer, and it's difficult to convince them. Therefore, we can omit this problem when we propose the configuration which provide the post-fault operation. So make some of the, change the connection of the transistors all the time, deliver the energy to end user. And the second, even more difficult, it's a short circuit situation, because we cannot deliver the same power during the short circuit to use some of the selective use of the fuses in the system. Otherwise, we have to build a very high power converter and use only partially power, what have no sense from the financial point of view. And this is even more complicated argument of the power system operator. So therefore, in our case, because we should deliver the power to the end user, sometimes much higher in case of the short circuit. Therefore, we propose the solution when each leg can be make a reconfiguration. So it means that it's not strictly fixed connections. We can connect as many legs as possible to one phase. So it can happen that, for example, only one leg is connected to phase A, but 5 legs from those sets of the legs are connected to phase B, and, for example, 5 or 8 are connected to phase C. So it means that distribution of the legs between phases are not equal. And also we are working in colleagues from Chile in another configuration of the transformer, which is the modular multi-level converter. Normally, modular multi-level converter has a connected modules like here on the one side of the converter and another side. But if there is a medium voltage to low voltage, then our idea was to keep this cascade connection of the modules here on the medium voltage side and parallel connection of the converters on the low voltage side. But if we have these sub-modules like here, there is a problem with circulating current between the modules. And in the control, we have to solve the problem to keep this circulating current under control. So you see that if we make some of the invention in the topology, sometimes they demand some of additional invention in the control. As I told, this modular system, because it's time running, maybe I will make it faster, shows that there are a lot of advantages of the modular system because we have the possibility to connect to different terminals, AC medium voltage, AC low voltage, DC medium voltage and DC low voltage. Moreover, that modular connections gives us a lot of advantages like scalability, efficiency, management, lower rating of the components, lower du by dt and di by dt, lower development cost and reliability, multiple conversion channels, service during operation, power routing, and redundancy. However, there are a lot of also problems, mainly with communication between the modules. So I think that the difficult point, it's moved from the power electronics sometimes to the communication, how to exchange the data between the modules. What I think is also interesting part of the research. Okay, so 5 minutes. Okay, I have the agreement of Dmitry. To prove that this is attractive solution for power system operators, therefore we investigate the operation on the medium voltage side. So you can therefore I distinguish here that there is a medium voltage side. Firstly, with analyzing how to use it in some of the subsystem module. This is IEEE model, including the 13 nodes. And what I can distinguish. So this subsystem, full subsystem, it's connecting by this point node 650. Yes, so they are probably different subsystems, but there is a connection point of this subsystem. And also important is this node 633, because this node connects the medium to low voltage transformer. So this is transformer which is usually close to our houses, which are deliver us the energy because we are end user somewhere here. And we would like to show the influence of the classical transformer on smart transformer to these 2 points in the subsystem in the nodes 633 and 650. By the way, Adam, the second guy who was drinking a coffee with us, did this research in deep, and therefore you can find some of the results in this paper, publishing Transactional Power Delivery. Have a note that there is a voltage in the node 650, there is a voltage in node in 633, so those voltages. And here we have the classical transformer and smart transformer. So once it's a classical and once it's a smart transformer. And how looks the current in node 650? So if the current was distorted here, because we have non-linear load, so also this distortion somehow it's also influencing the point 650. But because the smart transformer provides us really sinusoidal and balanced current, what we have seen here, 633, so you can see that the current is also sinusoidal in the node 650. So I think it's an advantage for the colleagues from power system, showing that there is nice work replacing the classical transformer by the smart transformer. The another option, which is for us, it's only the sum of the additional lines in the algorithm, in the microcontroller, that on demand on the power system, we can provide that we have, for example, when we have the voltage sag, please pay attention that we have the voltage sags on this green voltage shown here. So the amplitude is much lower than the red and blue. In such situation, we have the three scenarios, possible scenarios. It's up to us. One, that we keep the constant power. So it means that the current is higher in the phase green. We have the symmetrical grid currents all the time. Or we have grid support by fast unloading. It means that probably this voltage drop was because there is a short circuit somewhere in the system. So this unload this phase shortly, and we unload this amplitude of the current, it's lower. So it's up to us. It's only, as I told, what we propose in our algorithm. Okay, maybe I will switch this faster. But the idea here is, as I told, that we can connect or reconnect the legs to the phases which are overloaded. So if the phase L1 is overloaded, so I can connect more legs to this phase L1. What I think it can be some of the argument for the power system operators, especially that there is a problem of a short circuit with the smart transformer. And you can see there are some of the research which was done by us in our research team. So there is a symmetrical, by the way, from the top there's low voltage, there is a voltage on the one module because we use the two modules for that, the second module, and we have the currents in the one module and the second module, and the output current. And what we can observe, until now everything was perfect. Then the one phase was overloaded. You can see the overloaded. Then we turn off two branches in one module. Then we change those the two branches to another phases. We again turn this reconnected phases. And finally, we come back to the balanced system. So it means through the reconfiguration, we are able to skip the problem which appears in the system. Okay, of course, the control is very complicated. If we are talking about only the modulation or the current control, it's nothing, because it's usually everything it's provided by this cell control. So very easy, but we have some of the hierarchical control. So usually the control including many of the functionalities like active and reactive power, harmonic compensation, load identification on the low voltage side. So there are plenty solutions. I think that each of them can be the subject for the separate lecture. So I'm not going to extend my lecture today to these elements. But let's come back to the problem of the short circuit capability. So one of the options, which I think it's very promising, is that between the classical transformer and the smart transformer, so we'll have some intermediate step. This intermediate step, it's a hybrid transformer. It means that parallel to the classical transformer, we have the power electronics system. And in case of the short circuit, the main power which have to be delivered during the short circuit, it comes from the classical transformer. And there are some of the works showing that it can be used for the renewable energy sources, for electromobility. Also, they are existing already in the research labs solution with some of the extra winding, like here, with this connection, what you see to the secondary side, which is, of course, very attractive. And even in the group of the Collar, they built some of the such prototype of hybrid transformer. However, there are some of the drawbacks of this system, and therefore our idea, which are developing in our lab, by the way, I have one of the PhD students from Chile who is doing this research in my lab currently, that we connect AC, DC AC converter as a series and shunt active filter. And what gives the advantage? That you can notice that if there is a problem with the grid voltage, if the voltage is suddenly here distorted, so we can compensate this voltage distortion of the voltage. So through this compensation, on the secondary side, the voltage is all the time sinusoidal. Also, we can tell, okay, but it brings some of the lower efficiency because this converter, moreover, that there is some of the circulation of the power also, they bring the lower efficiency of the system. But at the same time, because we reject some of the higher harmonics, which can go through the transformer, we improve the efficiency of the transformer. So I think we not made the final investigation, experimental investigation, but our expectation is that the total efficiency during the distortion will be the same, because what we lost for circulating power, we reduce the losses in the transformer. And as far as I remember, it's one of the last slides. I will not later on summarize everything, because I think that most of the summary I told you somewhere between, but have a look for the system when in the output was the nonlinear load. You can see that there is a nonlinear load, and we compensate this nonlinear load by the shunt active filter, and at the same time we compensate here the voltage drop by series filter. And secondary current, it's a fully sinusoidal. So I think and I believe that there is a future, maybe conclusions, as I told, that more or less I give you the conclusions between presenting the different technologies. So you can see where we can use the power electronics as a summary. Thank you very much.